Good afternoon. In our lessons, we will learn about why balloons pops up and so on. We can find answers to your lots of questions. Our topic is ideal gas laws. My name is Zhangozy Ongarbay. I'm a physics teacher of Ongarbay Intellectual School of Physics and Maths in Kokshetau. Our lesson objectives. And our learning outcomes. You will be able to describe kinetic theory and model of ideal gas. After our lesson, you can explain the gas laws PV equal NKT, Boyle's law, Charles' law, and Gay-Lussac's law. Explain how molecular movement causes a pressure exerted by gas and hence deduce a relationship. And compare two equations, PV 1/3 and then 0 V squared and PV equal NKT. And from this equation, hence deduce that average kinetic energy of a gas molecule is proportional to temperature. Before explaining gas laws and its kinetic theory, let's recap what are gases.
Gas. The state of matter in which particles are widely separated and are in constant random motion. Particles in a gas have more energy than in a liquid or solid and move about to fill the container they're in. Gases can flow and can be compressed. In theory, any chemical can exist as a gas given the right temperature, provided it does not break down chemically first.
Ideal gas laws, absolute temperature, absolute temperature, pressure, kısım, volume, coulomb, Avogadro's number, Avogadro sana, mole, universal gas constant, universal gas traktisi, kinetic theory, kinetical theory, және орташа квадратчыланды, root mean square speed. Now, let's work in your group. In your group, please investigate following questions. I'll give you instructions for your groups. Please use posters and markers, and in your book, page 367, yeah?
Yes.
Group 1, 369, group 2, and 372 for group 3. Is it clear?
Yeah.
Any questions?
No questions.
Okay, thank you. Let's start. You got 15 minutes. Is it enough for you? 15.
Yes.
Okay, 15 minutes.
the gas laws and absolute temperature. Our task was to explain the Boyle's laws, Charles' law and Gay-Lussac's law, and give an explanation to the absolute temperature term. First is Charles' law. Given graph shows that the graph of the volume temperature versus of the volume of the gas versus temperature gives us a straight line that crosses the origin. And compared to that, we can say that the Charles' law states that the volume of a fixed quantity of a gas is directly proportional to the absolute temperature when the pressure is constant. So in Charles' law, V, volume of the gas, is directly proportional to the temperature of the gas, and P is always constant.
The second law is a Boyle's law. The volume of a gas is inversely proportional to the absolute pressure applied to it when the temperature is kept constant. You can see that in that graph. And where P is the absolute pressure, and for example, if the pressure on a gas is doubled, the volume is reduced to half its original volume. Gay-Lussac's law. Gay-Lussac's law states that at constant volume, the absolute pressure of a fixed quantity of a gas is directly proportional to the absolute temperature, where the V is constant.
I'm going to explain the absolute temperature term. Absolute temperature is absolute zero temperature in kelvins. 0 kelvins is absolute temperature, and in Celsius it's minus 273.15 degrees, and it is the lowest temperature possible. Now many explorations are giving the information that that is so, and this is the lowest temperature possible.
All we know the laws of gases like Boyle's, Charles, and Gay-Lussac laws. So we can combine these laws into one proportion, like P, pressure and volume are directly proportional to mass, M, and temperature. At constant temperature and pressure, the volume of an enclosed gas increases in direct proportion to the mass M of gas present. So, using this proportion, we can deduce the ideal gas law. The formula and equation of ideal gas law presented like that. Pressure multiplied by volume is equal to N multiplied by R and T. So we have this pressure. We should give pressure in. We should give absolute pressure and temperature in kelvins. It is important. And then we have an universal gas constant, the number of moles, and volume.
And we use the term ideal because real gases don't follow this equation precisely, particularly at high pressure. Second, what is a mole? The mole is an official SI unit for the amount of substance. 1 mole is the amount of substance that contains 6.02 multiple to 10 powers of 23 objects. And mole is equal to mass divided by the molecular mass.
The third question is about what is the universal gas constant. The universal gas constant is a required amount of heat when we heat 1 mole up to 1 Kelvin temperature.
Thank you.
The ideal gas law in terms of molecules, Avogadro's number. Radamel Avogadro, he is Italian scientist. He was born in 1776 and died in 1856. Avogadro states that equal volumes of gas at the same pressure and temperature contain equal numbers of molecules. Someone calls it Avogadro's hypothesis.
The main formula is PV equal T. P is pressure, V is volume, N is number of molecules, K is Boltzmann constant, and T is temperature. The number of molecules in 1 mole of any pure substance is known as Avogadro's number, Na equal 6.02 power 10 of power 23.
And here, total number of molecules is equal to Avogadro's number times M. And therefore, ideal gas law can be written by this formula, and total formula is PV either equal to NKT because K is Boltzmann constant and it's equal to R over NA.
The owner's manual that comes with every car states the proper pressure for the car's tires. These figures are called pressure and thus should be measured before driving the car. Why? Because after you drive the car a while, the temperature of tires increases and therefore, according to the gas law we have studied, the pressure of the tires also increases because the volume remains relatively constant. Although we can explain the relationship involving the pressure and temperature of an ideal gas on a macroscopic level by using our gas laws, we have not yet fully described what is happening in gases on a molecular level. How can the properties of pressure and temperature be described in terms of the molecular properties of a gas? A concept known as kinetic theory does an admirable job of describing these characteristics. The basic premise of kinetic theory is that matter is made up of atoms and molecules that are constant random motion. In formulating kinetic theory for ideal gases, we must take certain assumptions regarding the molecules making up the gas. The first is that gas is made up of randomly moving molecules. Gas molecules are usually very apart from one another relative to their size. We assume that gas molecules interact only by collisions and that these collisions obey the laws of Newtonian mechanics. Finally, kinetic theory assumes that collisions between molecules or between a molecule and the wall of a container are elastic. The pressure a gas exerts on the walls of a container is a result of molecules colliding with the walls. If we assume collisions with the wall are elastic, each molecule of mass m exerts a force on the wall with a magnitude equal to the time rate of change of molecules x components of momentum. After bouncing off the wall of the container, molecules may again collide with the container. The time interval between the collisions with one wall is related to the x component of molecules' speed and the distance between the wall. We can thus write the force on the wall in terms of a square of the molecule's x component of velocity and the distance between the opposite walls. The random motion of many molecules is needed to produce a relatively constant force on the container wall. Therefore, the net force is related to the total number of molecules and the average value of square of x component of velocity of those molecules. Because the velocities of the gas molecules are assumed to be random, the average value of square of velocity of the gas molecules can be related to that for the square of x component of the velocity. Remember that pressure is equal to the force per unit area. Thus, since the volume of our container is its length times the area of its face, We can derive an equation for the pressure of gas in terms of its molecular properties. Our derivation is valid even though we ignored collisions between molecules. Statistically, such collisions average out and therefore they do not affect the number of collisions with the container wall. Our result is also independent of the shape of the container. Now, by multiplying both sides of our pressure equations by volume and combining the result with the ideal gas law, we can relate the temperature of the gas to its molecular properties. You can see that average kinetic energy of the gas molecules is directly proportional to the absolute temperature. This relationship can also be applied to liquids and solids, thereby providing us with a quantitative explanation of why molecules making up a substance move faster when the temperature of substance increases. We can calculate now fast on average molecules are moving by taking the square root of average of the square of molecular speed. This is known as the root mean square speed of the molecules. Let's calculate the root mean square speed of helium atom in a balloon at room temperature of 293 kelvins. First, we calculate the mass of one molecule of helium gas by dividing its atomic mass by Avogadro number. Plugging this into our equation, we see that the root mean square speed of the helium atom is a very fast 1350. So, we are going to now work out some examples on gas loss. First example, volume of 1 mole at STP. Determine the volume of 1 mole of any gas, assuming it behaves like an ideal gas at STP. First of all, STP, it means standard temperature and pressure. So, we know 1 mole, so N is 1 mole. Standard pressure is 1 atm, 1013 10 power of 5 Newton meter squared. So standard temperature is 273 kelvins or 0 Celsius. Now we need to calculate the volume of gas. So we use the ideal gas law solving for V, ideal gas law. PV equal nRT. So from that equation, V equals nRT over P. So let's calculate. V equal N is 1 mole times R is universal gas constant 831 joule over mole times Kelvin times temperature is 273 kelvins over standard pressure is 1013 times 10 power of 5 Newton meter squared. So if we use our calculator, the answer will be 831 times 273 over 1013. So answer is 22, 39 and 5 10 power of minus 5 meter cubed. So answer is V equal 22 and 4 10 power of minus 3 meter cubed. So it means since 1 liter is 1000 centimeter cubed, 1 mole of any gas has V equal 22 and 4 liters at STP. Example number 2. Helium balloon. A helium balloon assumed to be a perfect sphere has a radius of 18 centimeters. At room temperature 20 degrees, its internal pressure is 105 atm. Find the number of moles of helium in balloon and the mass of helium needed to inflate the balloon to these values. First of all, we know it's given radius, it's 18 centimeters, temperature 20 degrees, and pressure is 105 atm. First of all, we need to convert these values into SI values. SI, 18 centimeters is 018 meters. 20 degrees is plus 273, it's 293 kelvins. So 1 atm is 105, 10 power of 5 Newton meter squared. So we need to find number of moles and the mass of helium. So we can use the ideal gas law to find N. So ideal gas law is PV equal nRT. So from that equation, N equal PV over RT. So we know the pressure, we know the temperature, we know the R universal gas constant, but we don't know the volume. So it says in our task, assumed to be perfect sphere. It means volume of sphere is 4 over 3 pi r cubed. So let's calculate the first of all volume. 4 over 3 pi r cubed. Pi r is 018 meters cubed. So it could be 018 times 018 times 018, it's 005 times 4 over 3. So answer is 0.0 times pi, 3.14, 0.0244 meter cubed. So now let's calculate the number of moles. Number of moles is N equal 105 10 power of 5 Newton meter squared times volume is 0.0244 meter cubed over R is 831, universal gas constant, Joule, mole times Kelvin times 293 kelvins. So an answer is 105 times 100444 over 831 293. So answer is 1066 mole. The mass of helium using the periodic table, the atomic mass of helium is 4 grams over mole. So mass could be defined, mass is number of moles times molecular mass. So it means 1066 mole times 4 gram moles. Moles are cancelling out, so 426 grams. Answer is 1066 mole and mass is 426 grams. Example number 3. Mass of air in a room. Estimate the mass of air in a room whose dimensions are 5 meters times 3 meters and 2.5 meters high at STP. So, first we determine the number of moles using the given volume. Then we can multiply by the mass of 1 mole to get the total mass. So, 1 mole is as we mentioned it, 1 mole at 0 degrees. 1 mole at 0 degrees. It has volume 22.4 liters. So, room's total volume is 5 times 3 times 2.5 meters. So it means, number of volumes is volume 5 times 3 times 2.5 meters over 22.4. It's in liters, we need to convert meter cubed. 10 power of minus 3 meter cubed. So 5 times 3 times 2.5 over 22.4. So it's approximately 1,001.7674 10 power of 3 moles, or approximately it's 107,000 moles. So, again, now we need to estimate the mass of air. So air is a mixture of about 20% of oxygen and 80% of nitrogen. The molecular masses, so molecular mass is about O2, oxygen 2 is 32 units, and molecular mass is nitrogen 2 is 14 times 2 is 28 units. So, respectively, so average value is approximately 29 units. Thus, 1 mole A has a mass about 29 grams or 0.29 kilograms. So now we can calculate the estimate average mass of air. Mass equal, okay, it's estimate 1000 mole times 0.029 kilogram moles. So it's approximately 1000 times 0.029, 49 and 3 kilograms. It's approximately 50 kilograms. Average mass of in our room is approximately 50 kilograms. Example number 4. Check tires cold. An automobile tire is filled to a gauge pressure of 200 kilopascals at 10 degrees. After a drive of 100 kilometers, the temperature within the tire rises to 40 degrees. What is the pressure within the tire now? We don't know the number of moles of gas of the volume of the tire, but we assume they are constant. We use the ratio form of the ideal gas law. So let's assume volume is constant. Volume is constant. So if volume is constant, gas law P over T would be constant, or P1, T1 equals P2 and T2. So this is inevitably, so Gay-Lussac's law. Gay-Lussac's law. So, since it says pressure is gauge pressure, so in our Gay-Lussac's law, pressure must be absolute pressure or atmospheric pressure plus absolute pressure. Absolute pressure is gauge pressure plus atmospheric pressure. So P1 is equal P gauge plus P atmospheric. So it's equal 200 kilopascals plus atmospheric pressure is 101 kilopascals. So it's 301 kilopascal. Using Gay-Lussac's law, now we can calculate the second pressure. So P2 equals P1 T2 over T1. So it's P1 is 301 10 power of 5 pascals times, so assuming these are absolute temperatures. Now we need to convert Celsius into Kelvins. So (313) Kelvins over 40 degrees, it's 330. 10 degrees, it's 283 kelvins. So it's 313 over 283. 1111 times 301. It's almost 333 kilopascals. So, subtracting atmospheric pressure, we can find the atmospheric pressure here. So subtracting atmospheric pressure, it's gauge pressure. So P2 equals 333 minus kilopascals minus 101 kilopascals. So it means 232 kilopascals. So that's why in every car manual suggests checking tire pressure when the tires are cold. Outline of our lesson. Today we talked about ideal gas laws. The main ideal gas law is PV over T is constant. From that equation we can derive three ideal gas laws. The graph of isovolumetric process, the graph of isothermal process, and the graph of isobaric process. Also we talked about ideal gas law in terms of molecules. Gas law is P 1 over 3 and mv squared, and we compared these two equations and deduced that average kinetic energy of a molecule is proportional to the pressure, or it's directly proportional to the temperature. Your homework is, there are two balloons. One of them is fully inflated, second one is partially inflated. They are connected via tube with a valve in it. What happens when the valve is opened? Think carefully. Try to do this experiment. Thank you. See you next week.